Okay, for the Brayton cycle, the turbine exhaust temperature is normally greater than the compressor exit temperature because even though the temperature rises when air being compressed, but it is not sufficient enough to have heat addition where it happened in the combustion chamber, where heat being added, the combustion process increases the temperature of the air before it goes into the turbine. Therefore, heat exchanger can be placed between the hot gases leaving the turbine and the cooler gases leaving the compressor. So we call this as a regenerator or recuperator. Okay, as shown in this figure 39, a figure of gas turbine engine with regenerator. You imagine there's air coming into the compressor from one. This is a compressor inlet, and as it exits from the compressor, it will go through a regenerator. Okay, so the heat, there will be heat addition into the system. Before this, we do not have that. Okay, so we have the regenerator to increase the temperature at a more suitable temperature for the combustion process to take place, right? And the flow then go into the turbine, and the air will then exited the turbine, will also pass through the regenerator, where the heat being then expelled out of the system, go back into the process of from 2 to 5. And you can see that it is a continuous process. Okay, so and this is the TS diagram in association with the Brayton cycle with regeneration. So we define the regenerator effectiveness, or eta regen. We can have E regen over here as the ratio of the heat transferred to the compressor gases in the regenerator to maximum possible heat transfer to the compressor gases, right? So the heat being transferred in the regenerator actual, and we also have regenerator max. We have the H5 minus H2 over here, where H5 prime, you can see the symbol prime there, minus H2. Okay, in this case it is equal to H4 minus H2. Okay, the effectiveness of the regenerator is equal to the Q regen actual over Q regen max. So you can have that expression to find the regenerator effectiveness. For ideal gases, using the whole air standard assumption with constant specific heat, the regenerator effectiveness already become this expression. Instead of H5 minus H2 over H4 minus H2, we can then rewrite it to be equal to the temperature difference between 5 and 2 and 4 and 2. So bear in mind, 5 is a station before it goes to the combustion chamber, right? This is the new thing, okay? And the rest are the same. So 2 is the compressor outlet, 4 is the turbine outlet. So using the closed cycle analysis and treating the heat addition and heat rejection as steady flow processes, the regenerative cycle thermal efficiency can be rewritten as follows. So we want to write the expression of Q out. In this case, Q out is H6. Okay, Q out H6 minus H1, Q in H3 minus H5. If you refer back to the figure here, right? H6 is basically the point where the heat being rejected from the system into back to the system. Q H6 to H1 over here. Okay, right? Notice that the heat transfer occurring within the regenerator is not included in the efficiency calculation. Okay, because this energy is not heat transferred across the cycle boundary. So that's a very important thing to take note. Assuming ideal regenerator where the efficiency of the regen equal to 1. We assume it is perfect. Okay, ideal regenerator. And constant specific heat, the thermal efficiency can be written as follows. The pressure ratio as well in term of temperature between 1 and 3. So when does the efficiency of the air standard cycle Brayton cycle equal to the efficiency of the air standard regenerative Brayton cycle? So if we set the Brayton cycle thermal efficiency equal to the regenerator thermal efficiency, then we can get this expression. You just put down the Brayton cycle thermal efficiency component and the regenerator thermal efficiency component and rephrase it, or you get the component of RP to be on the left hand side, and you can get this expression of the temperature ratio of T3 over T1. So you can then recall that this pressure ratio that maximizes the network for the simple Brayton cycle and makes the T4 equal to T2. You want to make the temperature at exit turbine equal to the temperature of the exit of the compressor. So we want it to be the maximum. What happens if the regenerative Brayton cycle operates at a pressure ratio larger than this value? For fixed T3 and T1, pressure ratio greater than this value cause T4 to be less than T1. And of course, the regenerator will not be effective anymore. Okay? There's a limitation in terms of the pressure ratio. The following shows a plot of regenerative Brayton cycle efficiency as a function of the pressure ratio RP and minimum to the maximum temperature ratio of T1 over T3. Okay, so you have the value of the thermal efficiency, Brayton thermal efficiency from 0.1 to 0.7, and you can also have the pressure ratio from 5, 10, 15, 20, 25 for the compressor. Okay, you can see here without regeneration, without regen, this is the Brayton cycle without regen value, and this is with regeneration. So you can see that for with regeneration at T1 over T3 equal to 0.33 and then 0.25, 0.2. You can see that it coincides also with the without regeneration. Okay, so you can see the limitation. Now let us look into another example. We have example 9.8 to determine the thermal efficiency of the gas turbine described in example 9.7, where the Brayton cycle is not operating at its ideal stage. We want to apply regenerator having an effectiveness of 80%. So the E equal to 80%. As a solution, right? This figure 942 is the TS diagram for the regenerative Brayton cycle described in example 9.8. For a specified effectiveness, the thermal efficiency also need to be determined. Right. We first determine the enthalpy of the air at the exit of the regenerator. So we use the effectiveness definition. We have not H5 minus H2A over H4A minus H2A. Okay. So effectiveness of the regenerator given already 80%, and we have the value of H2A 605.39. The enthalpy. Okay, you put down all the values here, and you will get H5 to be 825.37 kilojoule per kilogram. Then you can get the amount of heat being generated into the system. H3 minus H5, where you put the number of H5, you will get the heat into the system is 570.60 kilojoule per kilogram. So this represents a saving of 220 kilojoule from the heat input requirement, right? So the addition of regenerator, assumed to be frictionless, does not affect the network output. So the network output is still the same, but the net heat input is already different. So now the thermal efficiency is already raised to 36.9 from 26.6 in the earlier example where there is no regenerator. Now we already help the system to go up to 36.9%, which is a result of installing a regenerator. This is to recover some of the thermal energy of the exhaust gases, because it is a loop. The heat generated from the turbine then being supplied back to increase the thermal efficiency of the gas turbine engine. Okay, now we want to look into more complex system where instead of having regeneration only, we want to introduce intercooling, reheating, as well as regeneration at the same time. So the work output of a turbine operating between two pressure levels can be increased by expanding the gas in stages, as well as reheating it in between that, and utilizing multi-stage expansion with reheating. Right? You can introduce more regenerator. You can introduce more heating or cooling, and this is accomplished without raising the maximum temperature in the cycle. So you can have TH and TL. As the number of stages increase, the expansion becomes nearly isothermal. Right? The foregoing argument is based on a simple principle. What is the principle? The steady flow compression or expansion work is proportional to the specific volume of the fluid and the working fluid. In this case, we can call it as air only. Therefore, the specific volume of the working fluid should be as low as possible during the compression process and as high as possible during the expansion process. A schematic of the physical arrangement and the TS diagram of an ideal two-stage gas turbine cycle with intercooling, reheating, as well as regeneration is shown in the figure 944 and 945. And let us look into the figure. So this 944 showing gas turbine engine with two-stage compression. You have one compressor and another compressor where we put an intercooler in between, right? And then two-stage expansion with reheating, right? And regeneration, right? So two-stage expansion. So you have after the turbine, you have the reheater, another turbine, and then you have the regenerator to increase the thermal efficiency before it goes back to the combustion chamber and the turbine. Okay, as you can see that it is more complex now. This is the figure 945, the TS diagram. Again, the TS diagram also being more complicated. Okay, instead of a simple one cycle diagram, so we have the where the heat being heated many times. The air being heated many times from the compressor 1 to 2, and we have the intercooler, the heat being expelled out back, and we have the temperature raised again from 3 to 4 before it goes to the regenerator, right? The regenerator supplying more heat before it goes to the combustion chamber. 5, 6, 6, 7. We already go into the first turbine, and then 8, 9 we go to the second turbine, and 9 to 10, 10 to 1 is going back to the regenerator and coming back to the station 1. Okay, so it is more complex now. So for us to appreciate more, probably best to go into an example. Example 99. This ideal gas turbine engine with two stages of compression, two compressor, and two stages of expansion, two turbine, has an overall pressure ratio of 8, right? The RP equal to 8. Air enters each stage of the compressor at 300 Kelvin and each stage of the turbine at 1300 Kelvin. You have to determine the backwork ratio and then the thermal efficiency of this gas turbine cycle. We assume no regenerator and ideal regenerator. There are two situations here. One, without generator, and then another case B with ideal regenerator of 100% effectiveness, right? Where E equal to 1. You have to compare the result obtained in example 9.6 so that we can appreciate what happened when we introduce such thing. Solution: ideal gas turbine cycle with two stages of compression and two stages of expansion is considered. The backwork ratio and thermal efficiency of the cycle are to be determined for the case of no regeneration and maximum regeneration. Right. Assuming steady operation condition exists, air standard assumption applicable, air kinetic and potential energy changes are negligible. If you look at the TS diagram, okay, we put the numbers of the values 300 at station 1 and 3, right? And 1300 at the turbine inlet, 6 and 8. Okay, we note that the cycle involves two stages of expansion, two stages of compression, as well as regeneration. For the two-stage compression and expansion, okay, the work input is minimized and the work output is maximized for the compression and the expansion when both stages of the compressor and turbine have the same pressure ratio, of 8. So we can then use the value, okay, to get the value of P pressure ratio of 2 to 1 and 4 to 3 to become 2.83, and same goes here, pressure ratio of station 6, 7 and 8, 9 to become 2.83 as well. Right. The air enters each stage of the compressor at the same time and isotropic efficiency 100% in this case. Therefore, the temperature as well as the enthalpy of the air at each of the compression stage will be the same. A similar argument can be given for the turbine as well. So that's where at the inlet of compressor T1 equal to T3, H1 also equal to H3. Similarly, with the turbine at T6 equal to T8 and H6 equal to H8. Similarly, at the exit of the compressor at T2 equal to T4 and T7 equal to T9. Similarly with the enthalpy over there. Right. So under this condition, the work input to each stage of the compressor will be the same. So will the work output from each stage of the turbine. So in the absence of any regeneration, the back work ratio, and the thermal efficiency are determined from table A17. Okay, you can go into table A17 to look at what is the value for enthalpy and the Prandtl number at 1, at station 1 at 300 Kelvin, right? Okay, so you can get those value, right, at 300 Kelvin, so you can get the enthalpy, you get the PR value, right? So similarly for at station 2, right, so you can put the numbers, you read PR2 3.92. What do we mean by that? You read from PR where is the corresponding value of 3.92. What is the corresponding value of 0.12? If you read through the table over here, you can then get the temperature to be 403.3 Kelvin for PR equal to 3.92. And you get then read the corresponding enthalpy, and you do the same for um, temperature at 1300 Kelvin. You read from the table A17 what is the corresponding value of enthalpy and PR6. Then you use that to find the value for T7 and H7. Okay, after you got all the values, right, you put inside the expression for the work compressor and then the turbine as well, you can then get the net work. Okay, net work already obtained, then you can work out the Q in, which is equal to Q primary plus Q reheat, right, by inserting the value of the enthalpies. You can then get the amount of heat being inserted, heat addition into the system, right? Then you can work into the back work ratio, RBW, okay, to become 0.304 and thermal efficiency of the system to be 35.8%. Right? As a comparison of this result, which we obtained from example 9.6, where we only have single stage compression and single stage expansion, okay, reveals that the multi-stage compression with intercooling and multi-stage expansion with reheating improve the back work ratio from 0.403 to 0.304. Okay. However, the thermal efficiency drops from 42.6% to 35.8%. Okay. Therefore, intercooling and reheating are not recommended in gas turbine power plant unless there are regeneration. Okay. So with addition of regeneration, ideal regenerator, no pressure drop, 100% effectiveness, does not affect the compressor work and the turbine work. However, the net work output and the back work ratio of any ideal gas turbine are identical, whether there is a regenerator or not. A regenerator reduces the heat input requirement by preheating the air leaving the compressor using the hot exhaust gases. In an ideal regenerator, the compressed air is heated to the turbine exit temperature T9 before it enters the combustion chamber. And thus, under the air standard assumption H5 equal to H7, it is also equal to enthalpy at station 9. Right? So the heat input and the thermal efficiency, in this case where the regenerator being used, 100% regenerator, okay, you can get Q in equal to 685.28 kilojoule per kilogram. It makes the thermal efficiency for the new system to become 69.6%. It is improved a lot. Okay, so we take note that thermal efficiency almost double as a result of regeneration compared to the no regeneration. The overall effect of two-stage compression and expansion with intercooling, reheating, and regeneration on the thermal efficiency increase of 63%. As the number of compression and expansion increases, the cycle will approach Ericsson cycle, and the thermal efficiency approach will become 0.769. Okay, so we just use the value of TL and TH just now. So adding a second stage increase the thermal efficiency from 42.6, it jumped to 69.6%, an increase of 27 percentage point. This is significant increase in the efficiency and usually is well worth the extra cost associated with the second stage. However, adding more stages can increase the efficiency an additional 7.3% and usually cannot be justified economically. And so basically there are limitations, right? Okay, so we want to cover the next two subtopic, and one is the idle jet propulsion cycle, and then second law analysis of gas power cycle. Right. The aircraft gas turbine operates on an open cycle because we know aircraft we do not have a system where it is a closed cycle, because closed cycle require more component. So you can see commercial aircraft, gas turbine engine, or fighter aircraft, it is an open cycle. The idle jet propulsion cycle, which is differs from the simple idle Brayton cycle, where the gases are not expanded to the ambient pressure in the turbine. Instead, they are expanded to a pressure such that the power produced by the turbine is just sufficient to drive the compressor and the auxiliary equipment, such as small generator and hydraulic pump. That is, the network output of the jet propulsion cycle is zero. Right? So the gases that exit the turbine through the nozzle at relatively high pressure are subsequently accelerated to a nozzle, as shown in this particular figure, figure 948. High temperature and high pressure gases leaving the turbine and accelerated in the nozzle to provide thrust. Right? A schematic diagram of turbojet engine as well as the TS diagram being shown here. So normally air will go into the diffuser, where we call this as an inlet. It's then being slowed down into the compressor, pressure build up, and being prepared for the combustion chamber, heat being added, okay, and air being expanded in the turbine, air also being accelerated before it goes into the nozzle. Right? So that's how it reads from 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, and 6 back to 1. Okay? So the thrust developed in a turbojet engine is unbalanced force that caused by the difference between the momentum of the low velocity of air entering the engine, entering the inlet, and the high velocity exhaust gases leave the engine. And it is already determined in Newton's second law. Okay, you can recap back from our lecture number 2. Okay, the pressure at the inlet and the exit of the turbojet engine are identical. Okay, it is ambient pressure. So pressure exiting the nozzle will be the same as the pressure goes into the inlet, and thus the net thrust developed by the engine can be expressed by this equation 97. Okay, the net thrust F equal to mass flow rate times the velocity of the exit minus mass flow rate times the velocity of the inlet. Okay, basically mass flow rate is the same conservation of mass, okay, and the velocity difference between exit and the inlet. And the power developed from the thrust of the engine is normally called the propulsive power. We have the W dot propulsive power, W dot times the P pressure, which the propulsive force times the distance the force acts on the aircraft per unit time, as shown in here, where the propulsive power equal to the thrust times the velocity, from one point to another point. Okay, and can be expressed as the expression here 928, and the propulsive power unit is kilowatt. Okay, you have the mass flow times the velocity difference between exit and inlet times the velocity of the aircraft itself, right? So the desired output in a turbojet engine is the power produced to propel the aircraft. Okay, W dot P, and the required input is the heating value of the fuel itself. Okay, the Q dot in. So this ratio of these two quantities is called propulsive efficiency, zeta P, where zeta P equal to the propulsive power, W dot V, okay, over the energy input rate, okay, the Q dot in. And the propulsive efficiency is a measure of how efficient the thermal energy released during the combustion process is converted into the propulsive energy. Right? Right. The last part of the lecture today is going into the second law analysis of gas power cycle. Right? So I purposely didn't give example for either jet propulsion cycle, because the example given in this thermodynamic books is it is in English unit. I believe Dr. An will provide you with an example for using the SI unit, and maybe during the tutorial session for ideal jet propulsion cycle. So we will now move into second law analysis of gas power cycle before we end our session today. So we have already looked into the Carnot cycle, Ericsson cycle, Stirling cycle, Otto, Diesel, and Brayton. So we know that Carnot, Ericsson, and Stirling cycle are totally reversible, and thus they do not involve any irreversibilities. However, the Otto, Diesel, and Brayton cycle are only internally reversible, and they may involve irreversibilities external to the system. Okay? A second law analysis of this cycle reveals where the largest irreversibilities occur and where to start improvement. Right? So how we want to improve when there are irreversibilities associated to the system. The exergy destruction of a cycle is the sum of the exergy destruction of the processes that compose that cycle. So this is a definition on exergy destruction. The exergy destruction of a cycle can also be determined without tracing the individual processes, okay, by considering the entire cycle as a single process and using one of the relationship above, where entropy is a property and its value depends on the state only. For a cycle, reversible or actual, the initial and the final states are identical. So the entropy at the exit equal to entropy of the inlet, and therefore the exergy destruction of a cycle depends on the magnitude of the heat transfer with the high temperature as well as the low temperature reservoir involved and on their temperature. So it can be expressed on a unit mass basis as follows. So the expression 93, the exergy destruction equal to the temperature at station 0, okay, T0, okay, times the summation of the Q out over TB out minus Q in over TB in. The unit is kilojoule per kilogram. Example. So we want to look at the example 911 now. We want to consider an engine operate on an ideal Otto cycle. So given a compression ratio of 8, figure 957, right? This is the PV diagram, okay? And at the beginning of the compression process, right, from 1 to 2 compression process, volume uh, is being reduced, okay, but the pressure is increased. We start at 100 kilopascal at the temperature of 17 degrees Celsius, right, from 1 to 2. During the constant volume heat addition process, from 2 to 3, constant volume heat addition, 800 kilojoule per kilogram of heat is transferred to air from a source of 1700 Kelvin. So the temperature is 1700 Kelvin and waste heat is rejected at 300 Kelvin. The waste heat is rejected from 4 to 1. It's rejected at 300 Kelvin uh, of temperature. Okay. Accounting for the variation of specific heat of air with temperature, you have to determine what is the exergy destruction value, right, associated with each of the 4 processes and the cycle, and then the second law efficiency of the cycle. So for a solution, an engine operating ideal Otto cycle is considered. For specific source and sink temperatures, the exergy destruction associated with this cycle and the second law efficiency are to be determined. As you want to assume steady operating condition exists and kinetic and potential energy changes are negligible. Right. From the analysis, we take the engine bordering the heat source at temperature TH and the environment at temperature T0 as the system, right? So this cycle was analyzed in example 9.3 actually, Otto cycle, and the various quantities were given or determined to be as follows. So it is given the compression ratio of 8, temperature T0 at 70 degrees Celsius. So you convert into Kelvin, it comes to 290 Kelvin. T1 is also 290 Kelvin. And then T2, T3, and the remaining of the values. Okay. Right. Process 1 and 2, 3 and 4 are isotropic. So the entropy is the same. S1 equal to S2. S3 is also equal to S4. And therefore, it does not involve any internal or external irreversibilities. And that is the exergy destruction from 1 to 2 equal to 0. And exergy destruction for 3 to 4 equal to 0 as well. Right? For processes 2, 3, and 4, 1, constant volume heat addition and heat rejection process, right? They respectively and are internally reversible. However, the heat transfer between the working fluid and the source or sink take place through a finite temperature difference, rendering both process irreversible. When irreversible, we can calculate the value of exergy destruction. Right? The exergy destruction can be determined from equation 932. You have the value, the equation 932 over here, right? With subscript I and E denote the inlet and exit state respectively. So, but we want to find what is the entropy change, what is the S first, because you have to input the value of the entropy over here, right? So you have to find what is the entropy change during this process, from 2 to 3, okay? So you include the value of entropy at S3 naught and S2 naught over there. Okay, and inputting all the values, you get the difference between entropy at station 3 and 2 to become this value. Right. Also, you been given the value of the heat, constant heat addition, 800 kilojoule per kilogram, and temperature of the source to become to be 1700 Kelvin. Thus, you can put inside the equation 932 just now, and you will get the exergy destruction to become 82.2 kilojoule per kilogram for the process of 2 to 3. Okay. For process 4.1, right? So you can also do the same approach. You get the because S1 minus S4 is equal to S2 minus S3, entropy is the same, right? You get the same value over there. Okay, and Q for 1 equal to Q out, right? And the temperature TL, T sink equal to 290 Kelvin, right? Using the same equation, you will get the destructive exergy value, right, to become 162.2 kilojoule per kilogram. So therefore, the irreversibility of the cycle, the total irreversibility. So you have at station 1 and 2, 2 to 3, 3 to 4, and 4 to 1, where we know at 1 to 2 and 3 to 4, it is 0. Okay, and that's where we already calculated the exergy value for 2 to 3 and 4 to 1. Total is, for the cycle, is 245.4 kilojoule per kilogram, right? So the exergy destruction of the cycle could also be determined from another equation 924, and we can notice that the largest exergy destruction in the cycle occurs during the heat destruction from this process, the heat being rejected. Therefore, any attempt to reduce the exergy destruction should start with this process. You can improve the heat rejection process so that we can lower down the exergy destruction value. Okay. At the same time, the second law of efficiency is defined as the exergy recovered over the exergy expended. Okay, and you can rewrite it as 1 minus Ex destroyed over X expended, where over here expended energy is the energy content of the heat supplied to the air in the engine, which is its work potential, and the energy recovered is the net work output, right? So when you put inside the value, you will get the X recovered equal to the net work output equal to 418.17 kilojoule per kilogram, right? Substituting the second law efficiency of the cycle can be determined to become 63%. Second law efficiency can also be determined using exergy destruction data. So you can also get the same answer for this value, the efficiency to become 63% as well. Note that the exergy destruction associated with the heat transfer involving both the heat source and the environment are already accounted for these results. With that, I believe there are a lot of examples already been given, and I would highly recommend that you go back and try to go through the example that we have started last Friday, from lecture number 3 until today's lecture. So from all the example from gas power cycle, from the Carnot cycle, and then we have the Otto, we have the diesel, we have the Stirling, we have the Ericsson, we have the Brayton cycle until the Brayton cycle with regeneration, intercooling, as well as the reheating. So until what we had out today. So it's best to try to go through as many examples as possible so that you are familiar with the terminology and the equations that being used, especially when you want to track. I strongly suggest that you go through the example again and find the answers that are being shared in the examples, because you can easily make mistake by reading the wrong values in the table for A17, for example. So it's quite tricky, and it takes some time for you to be familiarized. So with that, okay, I think it's best for me to stop